Okay, so let's start. So let's continue to learn structural testing. And here is the outline. So let's have a quick recall of what we have learned yesterday. So basically, in this week, we are moving from black box testing towards white box testing. So, and we are getting access to the source code to better test the targets. And for black box testing, we know that the key is partitioning, right? Because the input space is kind of infinite. And for white box testing, the key is all about the different coverage metrics, right? So we have learned several different coverage metrics, and we can derive these metrics from the source code. And we are not deriving the metrics from the source code directly. We are trying to convert the source code into control flow graph. And then we derive the metrics based on the graph, right? And we have learned three metrics yesterday, four metrics actually. And now we are going to learn the fifth one, which is called path coverage. So what we have learned so far are that we have learned statement coverage, we have learned branch coverage, we have learned condition coverage, which could all be derived from this graph here. So statement coverage is related to covering all the basic blocks, and branch coverage is related to covering all the branches, and condition coverage is related to covering all the conditions. And we also learned the MCDC, which is a variation of condition coverage, which is also related to covering all the conditions here. And all these existing coverage we have learned are focusing on single elements. So whether it is a statement coverage or it's a branch coverage, they are all focusing on either the node or the edges, right? They are not focusing. However, when we execute the program, we need to execute a sequence of nodes and edges in the graph, right? So we learned that if we execute the program till exit, for example, this one here, we are actually executing a sequence of basic elements made up of nodes and edges. So, and this sequence here is called a path. So why not just use path as a new coverage metric, right? So we can use path as a new coverage metric here. And this gives us the path coverage. And the motivation here is that because it is a combination of different elements here, like it's a combination of different nodes and edges. So we can actually cover some specific patterns that are made up of some specific combinations. So the interaction between different elements, like different nodes and different edges, are therefore captured by this sequence here. So that's why we try to that's why path coverage is useful. And path coverage actually requires all the potential paths that goes through the control flow graph to be covered. So a path is like an execution sequence from the entry point all the way to the exit. And a path is made up of a sequence of nodes and edges. So this is the definition of path, and similar to other coverage metrics, the coverage of path coverage is calculated like this. So basically, we just use the number of paths covered by the test suite to divide it by the total number of paths. And here, let's do a quick warm-up live poll. So let's consider this flip sum function here. So basically, this function just takes an array and it just flip the value inside the array if the value is like satisfies is smaller than 0. So how many test cases do we need to cover all paths? We actually used this example to examine the number of test cases needed for edge coverage and for branch coverage and statement coverage, right? So we learned that because of this while loop here, we just need one test case to cover all the nodes and all the edges, right? But then how many test cases do we need to cover all the paths? Remember the definition of a path is a sequence of all the executed nodes and edges. And yeah, and let's see the results. And actually, most of you have got it wrong. So the correct answer is larger than 4, more than 4. The reason is that actually for for statement coverage or branch coverage, the loop actually helps us to reduce the number of test cases needed, right? But for paths, loop is actually getting us some trouble here because, for example, if we just exit the loop after looping it once, and if we exit the loop after looping it twice, do you think these two paths are the same? The blue one and the red one. Do you think they are the same? Yes or no? From the definition. So the definition is that it is a sequence of nodes and edges executed. So it's like a list of nodes and edges. So do you think these two are the same? They're not the same, right? Because it's a list of items. It's not a set of items. So a list of items means that this 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 right one is 1, 2, 3, 4, 5, 6. And this blue one is 1, 2, 3, 4, 5, and then 2, 3, 4, 5, 6. So the list can allow us to have duplicated items and list have sequences, and the sequence matters for lists, right? So the blue one and the red one are actually two different paths because of the difference of the elements inside the path. So that's why loops are giving us, because we don't know how many times do we need to loop here, right? So loops are giving us like sometimes infinite number of paths. And let's see here. So you may think, okay, since we don't know how many times do we need to loop here, what about we set a limit for the maximum number of times we loop here? So assume that we set the limit of the loop to be 100, but actually the number could be much higher, right? Because the loop can take the maximum number of the integer here. So assume that we limit the loop to 100 times. How many paths can we get? So every time, so every time we increase the loop count, we get a new path, right? And how many new paths do we get every time we expand we loop one more time? How many new passes can we get? It depends on how many paths do we have inside the loop, right? So in this case, we have two paths inside the loop. So this one and this one. So every time we loop one more time, we will get two more paths, right? And now we can loop 100 times. So how many paths can we get in total? Like it is 2 to the power of 100, right? So, and this is a number of 2 to the power of 100. And what if we have three different paths inside the loop? What if we have, let's assume we have another path here. What would be the number? It is 3 to the power of 100, right? It's even larger. So to let you know how large is this number is, so let's assume that we can. So if we try to cover all the paths by limiting the loop to 100 times, and let's assume that we can run 1,000 test cases per second, which means that we are running one test case per millisecond, and this will take us this number of years, and the life of Earth is like 4.5 billion years, and the billion is 10 to the power of 9. So you can see that this will take us like a longer time than the life of the Earth. So it is actually infeasible. It's infeasible to cover all the potential paths inside the program, especially when there are loops. So path coverage actually is theoretically the strongest coverage metric we can get for structural testing with control flow graph, and we can trigger some faults because of we are trying out different combinations of different nodes and edges. However, it is generally impossible to achieve 100% of path coverage just because of the problem. Then this problem is also known as the path explosion problem. So just because of this problem created by loops. And loop actually can give us, if we don't know how many times we can loop, it actually result in an infinite number in the path variations, because every time we loop, we can get a new path. And even if we bound the upper limit for the times we can get into the loop, we may still get an infeasible large number. Although it is not infinite, but it is still very large because of the branches. So every time we get into the branch, we will get into the loop, and if there's a branch, the number of paths doubles. So it is somehow infeasible to use path coverage in practice because we can't avoid branches and loops, right? But there are some ways to still get some benefit from the usage or from the idea of path coverage, and without like avoiding the cost of infinity or like an infeasibly large number. So can you think of a solution? What is like the key word, like the key solution here? So we have encountered the situation of infinity during the course, right? When we learn functional testing, we are dealing with an infinitely large space of inputs, right? We have infinite number of inputs. So how did we deal with infinity there? We do partitioning, right? So instead of trying out all the possibilities, which is impossible, instead of trying out everything, what we did was we tried to partition. I try to create partitions for the input space, and we try to select representative values from each partition, right? So what we can do is very similar here. Since we are dealing with an, a potentially infinite number of paths, what we can do is we can do some partitioning here. We can group paths together and select representative ones to create test cases. So this is how we derive some some practically useful strategies based on path coverage. So the first one we are going to learn is boundary interior coverage. So the key idea just now we learned that is because the number of paths could be infinite. So we have to somehow group them into different classes, right? And boundary interior is one of the ideas here. So for boundary interior coverage, what we do is we group the paths that differ only in the subpaths when following the repeating of the body of a loop. So instead of this is a little bit awkward. So let me try to make it simple. So in boundary interior coverage, what we do is instead of creating a new path every time we loop back, we just care about getting inside the loop once. And we just need to cover all the subpaths inside the loop once. And we don't care about expanding the path by looping back. So this is a key idea. And the rationale is like, because we can execute the loop as many times as we want, right? And sometimes getting into the loop once or twice makes no difference from getting it for more times, right? So that is the rationale. And let's take a look at an example here. So let's still consider this example here. So this time, this time we don't need to consider the case where we get into the loop multiple times. We just need to care about the number of subpaths we need to take. So there are actually two subpaths here, right? These are the two subpaths here. So how many test cases do you think we need to cover both of the subpaths at least once? So we don't consider like appending like maybe the pass. Let's assume this is pass one and this is pass two. So we don't if we loop multiple times, we may get like if we loop twice, we may get 1 1 1 2 2 1 and 2 2, right? But we don't care. We don't care about like looping it multiple. We don't care about whether the combinations, like the different combinations here. We just care about whether can we get both 1 and 2 covered. So how many test cases do you think do we need? We just need one test case. So because we don't care how many times do we loop, we just want to make sure that both 1 and 2 are covered at least once, right? So what we can do is we can still create a test case that loop here first, and then loop here, and then get out here. So we don't care about like the different permutations, different patterns, we don't care. We just need to care. We just need to make sure that we can cover both of them. So we can use just one test case here. So just to make sure that each subclass is covered. So that is why it is called boundary interior coverage, because we only care about what's happening inside the loops. We don't care about how many times do we loop. So this is the case, and this is an example input we can use for achieving this. So that's just a that's a simple example, and now let's consider a more complicated one. So you can see that we have a very big loop here, and let's try to get all the subpaths of the loop. And the first one is BM. BM is actually a special case, so we will talk about it later. And let's try to systematically go through all the potential subpaths. So BM is the first one, and if M is not an exit of the program, then we can consider BM as a subpath of the loop, which means that we are looping 0 times. So we just get out of the loop directly. And let's try to systematically get all the subpaths. So this is another potential subpath, right? And this is the third. This one is the fourth, fifth, and the sixth. So we can get 6 paths in total, right? We can get 6 subpaths in total. And what we did was DFS, right? Because we are getting into the leaf node first, right? And you can do a BFS for practice. And BM here, we need to be careful. If M is just an exit, then it's not a subpath. If, like, say, M is just an exit to the entire program, then we don't consider it as a subpath. But if it is not an exit for the entire program, then we consider it as looping 0 times. So this is the special case here. And boundary interior coverage, actually, we can see that it helps us to remove the problem of infinity for loops from loops, right? Because we don't care about how many times do we loop. However, the number of paths through the code could still be exponential, right? Because every branch can double the number of paths we have. And if we have, imagine if we have nested if conditions, then we can have to the power of something paths, right? So even we just care about the subpaths. So this may still lead us to some invisible amount of loops. So what we can do is, since we are still faced with potentially an invisibly large number, what we can do is we can further apply some limitations. And this leads us to the loop boundary coverage. So the loop boundary coverage focus on the problems or bugs related to the number of loops, the times that we loop. So it actually helps us to cover we can select representative numbers of times we take the loop. So the idea is for simple loops. So simple means there's no nested loop. So there's no like loop inside a loop. So simple loop is just there could be subpaths in the loop, but there are no other loops inside this loop. So for a simple loop, what we do is we can write test case that skip the loop entirely, which means that we are looping 0 times, right? And we can write a test case that take exactly one pass through the loop, which means that we are looping one time, right? We just loop once into the loop. And then we can write a test that run the loop more than one time. So these are the 3 necessary tests we need to have for loop boundary coverage. And optionally, we can choose an upper bound of for the loop because some loops, they naturally have an upper bound. For example, for for loops, we can easily get the upper bound of the loop, right? Most of the time. So we can choose an upper bound for this loop, and we can create test cases that pass the loop m times, where m is larger than 2 and smaller than the upper bound. And we can also test some values of n minus 1, exactly n, and n passes for the loop. And this is actually very, very similar to boundary value testing, right? To how we select values for boundary value testing, right? So because for loop, the mean value is by default 0, right? And this one here is somehow like mean plus, right? And this larger than 1 and this one and this m here, they are actually similar to the normal value for boundary value testing. And this one here, this n actually serves as the max value, right? And n minus 1 is max minus 1 and max minus, and n plus 1 is max plus, right? So it's very similar to how we select values for boundary value testing. And that's why it is called loop boundary coverage. And don't forget about the keyword here. This is for the simple loops where we don't have sub loops or we don't have loops inside a loop. And talking about loop boundary coverage, we can try to unfold the control flow graph to make the path look clearer across different iterations of the loop. So what we can do is, if we limit the iterations to 3, we can unfold this. We can try to unfold this entire loop body 3 times, and this is a control flow graph we can get by unfolding this. And the purpose of unfolding this control flow graph is that we can clearly see the different combinations of paths inside each iteration, right? For example, in iteration 1, we can take this path, and in iteration 2, we take this one, and in iteration 3, we take this one. So you can clearly see the paths across different iterations, rather than like drawing some circles there, which is not very clear. So this is just for clarity, because it makes no difference from the default control flow graph. And just now we covered the cases the case for simple loop, where we don't have nested loops. We don't have loops inside loops. So now let's consider the scenario of nested loops. So for nested loop here, as we can see, we have two loops. So this one here is actually F. So we have a smaller loop here. We have a larger loop here. So what we do is we consider them level by level. So first, what we can do is we can test the innermost loop first, and where the outer loop execute the minimum number of times. So which means that we fix the outer loop to execute maybe 0 times or maybe 1 times. Actually, it's at least 1 because we have to get inside the loop, right? So, but sometimes it's more complicated according to how the program is written. But we just try to execute, we just try to fix the number of times we execute the outermost loop. And then we can apply the special values we just learned in the previous slide to test the innermost loop. So the special values are like 0, 1, and more than 1, right? And then we move one loop out, and we keep the inner loop at the typical iteration. So which means that we take the value of more than 1. We take the normal value for the innermost loop, and then we try out different special values for the outer loop. And then we continue this iteration until we test the outermost loop. So this is the basic idea here. So let's try to practice with this example here. So what we can do is, let's just make sure that we take the outermost loop. Let's just take the outermost loop once, which means that we just see 1b here, right? And what we can do is we can skip, we can take the value of 0 here, right? So this is the case. And then we can take the value of we can take the value of 1 here because this one doesn't have a clear, we don't know which one is 0 or which one is what. So we can loop twice here, more than 1, and so on. We can take the special values. And then we finished, because we have finished trying out the special values for the innermost loop. What we can do is, for each test case, we can for a fixed value here, for normal value inside the innermost loop. This one is a little bit special because we don't know which, we don't have the actual code. We don't know whether there's an exit for this innermost loop or not. So we just select a typical value or just a normal value for the innermost loop and try to expand it with multiple iterations with some special number of iterations for the outer loop. So in this case, for the outer loop, we can take it 0 time. We can take it, take it 1 more time. We can take it 2 more times, and so on. So we just try out the special values for the outer loop as well. So this is the case here. And apart from nested loops, where we have loops inside the loop, we can also have concatenated loops. So where we chain some loops up. So in this case, if the loops are independent, it's very easy. We just test them one by one. So we just try out the special values we just go through the different loops and try out the special values for each one of them. So this is very straightforward, but sometimes they may not be independent, because some of the values, some of the conditions of a latter one may depend on the calculation of that value from the previous loop, right? So in this case, we start from the bottom loop. We start from the bottom loop and hold the higher loop to take the minimum iteration numbers because we have to because the condition of the bottom loop it depends on the calculation results from the higher loops, right? Because they are not independent. So we just fix the number of the higher loops and try out different values for the bottom loop. And then we can move up one by one. And this is somehow very similar to how we deal with nested loops, right? We deal with the innermost loop while fixing the value of the outer loop, and we move out one by one. So this is like how we deal with concatenated loops. So the design of these loop strategies, the basic purpose is just to, like the basic purpose is to do partitioning, right? To deal with the problem of infinity. And there are some other considerations for designing these loop strategies, which are somehow related to formal verification. So for formal verification, we have the preconditions, we have post conditions, and we have invariants. And this is just for your knowledge. You don't need to memorize anything on this slide, but this is like to expand the knowledge. So actually, the guy who proposed this, the logic is called Hoare logic, and that guy is also the inventor of quicksort, and he just passed away this year. So yeah, you can search for him. He's like the founder of this in this field. And why we take these special values like 0, 1, or more than 1. So if the loop executes 0 times, it means that the precondition means the precondition basically it means that the conditions are the values that must be satisfied before we execute the loop. And post conditions are like the constraints are the values that must be taken after we execute the loop. And invariants are some values that never change after, no matter how we, regardless of how we loop, like, or how many times do we loop. So this is invariant. So a simple precondition is like the condition guarding the loop, right? So the precondition must be false, or must be true for us to get into the loop, right? And the post condition is that the condition value guarding the loop turns into false, right? And invariant is like maybe the loop limit, like the upper limit. If we set the upper limit of the loop to be 10, then it will always remain to be 10, right? So this is a typical example of loop invariant. And if we loop 0 times, it means that the post conditions are true in advance, which means that, for example, in this example, where the guarding condition of the loop is already false before we get into the loop, right? So this is for post condition. And for loop invariant is like if we loop once, the loop invariant gets some value, right? The loop invariant takes some value. And if we loop many times, the loop invariant also takes the same value. Then we can say that, okay, this loop invariant is verified. So that's why we need to run the loop exactly once, and we also need to run the loop more than once. So So that's why, so the design of the special values here actually echoes the idea of this precondition, postcondition, and invariant. So it is not just for the consideration of boundary value testing, it is also to echo some formal aspects for program analysis. And before we talk about yet another partitioning approach, let's take maybe 10 minutes break, and I'll see you at 3:55.
So you said that we only have to submit the 5 rounds, but they need the bugs, right?
Yes.
Is that the question we want to do?
Yes, for both of them.
And then this other thing, for this input being written 50, some should be seated. Because for both of them, they're seated, but this one,
Let me track this back.
something a few days ago, but I didn't get a response.
And we already sent the email.
The CS 3142.
Oh, okay. Did you get a response?
No,
Okay.
and one.
I think because previously we were trying to apply some uh, additional conditions for exams, like you double the student count for exam, but we removed that. So I think lecture to and exam are all the same right
Yeah,
now.
so technically that should be a problem. Not
Yes. Yeah, it should be seated. But yeah, because the program was implemented
Yeah.
with that constraint, like for exams, we double the count.
okay.
That's the issue here. Yeah, let me check this. I will check with the consultant to fix this. Yeah.
And then, oh yeah, so just for question one, question two, you can just submit the first five.
Yes, yes.
And then I was going through the forum, and then the others were mentioning about, because question two has different types, right? Do we have to mention that, like that it should be an integer or it should be a float, or do we just give the numerical value?
You can just give us the numeric values because, like if if you uh, if you type like this,
Yeah.
it's like 1.0,
Yeah,
right?
yeah.
It automatically implies that
Okay.
it's a float.
Okay.
That,
Okay.
okay.
Thank you.
No worries. Okay, I think we can start because we have a lot of content to cover today. So, um, so just now we talked about several like two different types of two different approaches for doing the partitioning for paths, right? Because we have infinite numbers of paths, so we need to do some partitioning here. And just now we are doing the partitioning by grouping different paths together, right? So the first one is that we just don't care about the number of loops. We just try to take all the subpaths within the loops, right? That is called boundary interior coverage. And if we care about the number of loops we take, we we get the loop boundary coverage, right? Because we can take some special values for getting into the loop. But both of them are related to grouping the paths according to some criteria, right? What about we break up the paths into some segments and then combine these segments back into something that is back into something that is closer to the past. So this idea, this intuition leads us to this a new partitioning approach, which is called LCSAJ, which is also known as linear code sequences and jumps. So the key idea is that we try to get segments of paths on the execution path, and then we try to combine segments together to build some patterns and for us to test to cover. So this is the basic idea. And a linear code sequence and jump actually is used to describe a linear, because for basic block, remember the idea is that is a block of statements that will always execute together, right? And this segmentation here is actually very similar. So it is used to describe a linear block of statements that will always execute together. And the starting point uh, any given point, and it will end at a jump, like for if statements, loops, or function calls. Function calls are also considered as jumps here in this case. And then we try to identify where the jump leads. So this determines which segment we can connect together, right? And a single LCSAJ just covers one linear segment inside the control flow graph. So let's try to think about an example here. So for example here, so sometimes we can merge these B1, B2 together, right? But in some cases, in some notations, people may separate some basic blocks into several different ones for clarity. So just know that we can merge them together in this example here. So the first piece of so now let's try to, because we are trying to do the segmentation according to jumps, right? So let's try to identify the jumping points here inside this program. So what we have is we have three jumping points. We have the first one, which is the loop here. We have the second one here, and we have a third one here. And this one actually is very similar to the goto statement in assembly code or in C code. So what we do is we try to create segments based on the path, based on the control flow graph. So the first segment so by creating segments, we need to identify the starting point and the end point, right? The from point and the to point. So first we can start from the entry point and we can get to J1, right? And this will give us a sequence of basic block like this. And if we identify the entry and J2, we can get another sequence of basic blocks, right? So which is B1, B2, B3, B4, and B5. And can you imagine what is the next segment we can get? So we have entry to J1, entry to J2, and we can also have entry to J3, right? So if we build a segment, it is like this. So we can collect B1, B2, B3, B4, B5, and B6, B7 here to J3, right? So all these sequences here are just the segments we create. And then we can because we have tried out the all the cases where entry is the starting point. Now let's move on to use J1 as the starting point. So what we can do is we can try to use J1 all the way to the return here. And similarly, we can have J2 to J3, we can have J3 to J2, which is like, this is like how we can create the segments. And what we can do is we can then combine them together to build some patterns. And we try to create test cases that can cover these patterns. So this is the idea here. So because now we have each one of them is a single segment, right? And we can combine multiple segments together to create some patterns for us to cover. And we can set the number of segments we would like to connect to a number of n here. And this n, we can use this n to control the level of granularity here of this coverage. So if we set n equals to 1, then this coverage is actually equivalent to statement coverage because we are not combining any segments together. We are just trying to go through all the segments. And each segment is basically a sequence of like basic blocks, right? So because we are not combining any one of them, so it's kind of like we are doing a statement coverage. So if n equals to 1, it's similar to statement coverage. And what if n equals to 2? What is the equivalence here? So we are combining two segments together. And by combining two segments together, we are trying to cover the edges, right? We are trying to cover the edges connecting these statements. So if n equals to 2, then it's equivalent to branch coverage. And higher values of n can achieve stronger levels of path coverage. And we can define a threshold to offer strong test cases while keeping the budget affordable. So that is why we introduce LCE SAJ. And now let's try to practice what we have just learned for the path partitioning here. So let's think about this search function we used in our last lecture. So for this search function, it actually returns, remember the functionality of this search function. It actually takes it takes a string as the first input, A here, and it also takes the length of the string, and it takes a target character, and it returns the position of that character inside the string. And if that character doesn't appear in the string, this function will just return -1, right? So this is the search function here. And it is actually important for us to know the mechanism or the semantic of the target we are testing sometimes, and we will see why it is important later. So we can see that there is exactly one loop here, right? So how many subpaths do we have for this loop? How many subpaths? Because we are doing boundary interior coverage, we don't care how many times do we get into the loop, right? So we just care about the subpaths. So how many subpaths do we have? We have two, right? It's very clear, 7, 8, 10, and 7, 8, 9. So we have two subpaths here. So, and if we want to do boundary interior coverage, what we do is we just create a test case. We just create test cases that can cover both subpaths. And in this case, do you think we can use just one single test case to cover both subpaths? Is it possible? Yes. Actually, yes. The answer is yes. But the slides I didn't show the simplest answer. So what we can do is we can try to um, take the false branch here. We don't get out of the loop, and then we get back and take the true here. So this is the ideal test case we can get. So now let's consider how to practice loop boundary coverage. So how should we design the test cases here? So remember, when we design loop boundary test coverage, you see the keyword boundary, you can automatically think about like some boundary values, right? So we need to take some special values like 0, 1, more than 1. We need to take at least these 3 values to create test cases. However, do you think it is possible for us to execute the loop 0 times? So we need to take the value 0, 1, and more than 1. So do you think, assuming that we have reached the loop here, do you think we can loop 0 times in this case? Yes or no? Is it possible? I think most of you have finished. So let's see the result. And most of you have got it wrong. The answer is no. Uh, because because in order to reach the location of BB7, we have to be able to, let me show it here. Sorry. Oh. So in order to reach BB7, we have to take the true branch of BB6, right? So if we take the true branch of BB6, it means that n is larger than 1, right? And here in BB7, we check whether index is smaller than n, and we never touch the value of, we never assign new values to index along the path, right? So index is initialized as 0. And once we reach BB7, index will always be smaller than n here in this case. So in this example here, it is impossible for us. So although by definition we are required to create at least these three cases, right? The test cases that can trigger these three different situations. But in reality, we cannot create a test case to loop 0 times. So this is why we should, because we have the source code when we do structural testing, we should always consider how does the code work. So we should always think about the semantic of the code when we design test cases. So, okay, 0 doesn't work. What about 1? So can we loop exactly once? Can we run this loop exactly once? So index is 0 and n is at least 2, but can we loop exactly once? And every time index plus 1. If we don't consider this return here, it's impossible, right? It seems to be impossible to loop exactly once, right? But since we have this return here, so we can just get into the loop and take this. If there are returns and breaks, we can just get into the loop and break out, right? With the return or with the break. So we can loop exactly once. And these are this is an example for looping exactly once. So basically it means that the string is at least 2 bytes long, and the value of the character we are looking for is exactly the first character of the string. So in this case, we can break out the loop and just get into the loop and break out after we loop once. So this is the case. And if we want to loop twice, it's quite natural. So if we just don't let the first character of the string match the character we are searching for, and it will automatically loop back to search for the ideal character, right? So this is the example here. And this example is just to show you that we have to always consider the feasibility of the conditions along the path. So now let's continue. And we just learned uh, all the coverage metrics for structural testing. We learned we can use statement coverage, we can use branch coverage, we can use condition coverage, we can use path coverage. And we have learned several variations for all the different metrics. And now let's think about, do we have any limitations for applying all these techniques? So the first problem in practice is the infeasibility problem. And it is actually shown by the example we just learned right now, right? So sometimes we cannot get a suitable test to follow the requirement of the test case design. So for example, just now, um, by definition, we should create a test case that never gets into the inner loop. But in reality, because of the conflicts among the conditions, we cannot get a suitable test case. So that's the first case, and we just shown it could be due to the impossible combinations of conditions, and there are some other scenarios. For example, we may we may do defensive programming, And in this defensive programming, we are trying to catch all the potential errors, but some error handling code could be like over overly defensive so that the conditions may never happen in reality. So we cannot trigger that error handling pass in some cases. So there could be some cases where we cannot create any suitable test cases. And there could be some dead code as well. So for example, in some legacy applications, after doing some refactoring, we may make some of the helper functions to be legacy code or dead code, which are never used again inside the program. So these places are never reachable, right? And there could be some inaccessible portions for the off-the-shelf systems. That's because of many different reasons. For example, some of the systems may require some authentications to access certain part of the functions. So we may not be able to get past that. So these are all the potential reasons for not being able to create a test case to reach certain locations in code. And we have to address this problem in practice. And here are some solutions. So the first one is instead of trying to target 100% of coverage, we can have some we can have some thresholds instead. So instead of trying to always achieve 100% of coverage, we can try to achieve maybe 95%, maybe 80%, etc. So we can just use a threshold which is lower than 100. And once we have achieved this threshold, we can just stop. And sometimes we can also try to prioritize the creation of test cases as well, because elements are not equally important for fault finding. Maybe we'll learn about this later. So because sometimes some locations inside the program are more complex and some logic are very simple. So we can just focus on creating test cases for the complicated cases, and we can ignore the simpler parts of the code. And the second approach is that we can, like what we did for that example, we just manually inspected the case, right? We just manually go through the execution path, and we just checked, okay, we just manually confirmed that it is impossible to create a test case to never enter that loop. So we can do some manual justifications for these impossible cases. So this is also a practical solution here, but it could be very, very time consuming as we can imagine, right? So what happens in reality is that most of the time the companies will just stop testing when the money allocated for the testing team has been used up, or when the deadline for releasing the software is reached. So that's what happens in reality. So it's all about the budget we have, right? So this is the invisibility problem. And now, since we have learned all these different metrics, let's try to compare them. So for path coverage, we know that it is often infeasible, right? It is impossible because of the path explosion problem. We can have infinite number of paths, right? Especially when we have loops, and even if the loop has an upper limit, there could be path explosion problem because of the branches inside the loop, right? So path coverage is, although it is like the strongest metric here, it is often impractical. We cannot use them. And we have three variants of path coverage, right? So if we just consider all the subpaths and we don't care about how many times do we execute the loop, we can use boundary interior testing, which also suffers from the path explosion problem if there are many if-else branches inside the loop, right? So every time we encounter a branch, it doubles the count of the path, right? So this is also sometimes impractical. And for loop boundary testing, it is very, very manageable, right? Because we just care about looping for some special times, right? We just care about looping 0 times, looping one exactly once, and looping more than once, right? So this is more manageable. However, in practice, this will not lead to exactly just 3 test cases because we just seen that, okay, sometimes it's impossible to create some test cases. And sometimes because of the nested loops, because of the concatenated loops, we may create more test cases for loop boundary testing. And for LCSAJ, actually the position of this LCSAJ, it determines on the number of n, right? Because we need to decide how many segments do we want to combine together to build test cases. If n equals to 1, then it's somehow very similar to statement coverage. If n equals to 2, then it's kind of the same as branch coverage. If n is larger, we are moving closer to full path coverage. So this is LCSAJ. And there are some variations for branch coverage as well. So for branch coverage, we also have the basic condition. We have the condition coverage, right? Condition coverage is like instead of just taking care of the conditions that are used for branching, we consider all the conditions used. And sometimes conditions are not used just for branching. We can use it for calculating some Boolean values, right? So what we can do is we can do basic condition coverage, which means that we just try to cover all the true and false cases for each condition. And we can have this, and this is not something here. You can ignore this one here. And we can also try to consider MCDC, right? And we can also try to consider this compound condition coverage. So which means that we are trying out all the permutations, all the combinations of every true and false value for all the conditions, right? So this is the case, and MCDC is to apply some restrictions for compound condition coverage, which can give us a fewer number of test cases. So this is like a basic comparison of all the coverage metrics we have learned so far. And the rationale of all the coverage is that we cannot reveal an error inside the code if we are never exercising that part of the code, right? So this is true because it's never able, if the statement has some error and our test case can never reach this statement, then we can definitely, and then our test case cannot reveal the error, right? But is this the reverse of this true? Is also true. Like if we execute certain statements, we can always find errors inside them. Is this true or not? If we run the program, if our test case can maybe trigger some statement, are we going to always find the errors inside? The answer is no, right? Because Because for example, let's say we have an array of size 10. So the largest element we can access is the largest index we can use for accessing the array element is 9, right? And let's assume that we use I here and we put it into a loop, maybe a for loop. And we try to read the value here, and maybe we try to write to this array. So we try to write some values to this array. And by executing this line of code, we may not be able to trigger the bug. If I is larger than 9, then we are going to trigger the bug. If I is smaller than or equal to 9, then we are not going to trigger the bug. So by executing this single line of code, even if we execute it, we may or may not find the bug, right? We may or may not trigger some errors, right? Just because it also depends on how are we executing the statement. What values are used for executing the statement. So it is true that we have to execute the statement to find the bug, but it is not true that if we execute the statement, we will certainly find bugs inside. So executing a line containing a failure does not guarantee a failure. So even if we can achieve, this means that even if we can achieve 100% of path coverage, we may not be able, we are still not able to find bugs sometimes. For example, here's another example. So let's assume that we have a condition of A is smaller than or equal to B, and maybe the developer just made a typo and typed it as A is larger than or equal to B. And if the test case just use the case A equals to B, then we can always cover the execution of this condition here, right? And we are not able to find the bug, right? This is another example. So it depends on the values we are using in the test case as well. So this means that executing all the paths may not guarantee the finding of all bugs. So it also depends on the value of inputs we use. So that's why we need to care about the actual values used for executing the program as well. So that's why other than control flow determines how the order of executing the program, right? So other than just caring about the order of executing the programs, we should also care about the data flow. But in this course, we will just do an introduction to the data flow related concepts. And you can practice. There's another course which is 6131. You can take that course if you're interested in more in this concept. So data flow is like this. So program statements are like, we have learned that statements is like a concept for imperative programming languages, where each statement is like an instruction given to the computer, right? And after the computer takes this instruction, it actually, what the computer does is that it takes the instruction and follows the instruction to compute and transform some data, right? So what we care for control flow is we can try to look into how the data is passed through the program. So this is the idea here. And everything we do for control flow is to reason about the data dependency. And for example, if we see a value is used in some statements, what we want to reason about is we want to know where does the value come from, right? And we also care about whether this value is ever, if we declare a value, let's say if we try to declare a variable, and what we want to care about is we can try to see if this declared variable is ever used or not. And if we can also check if we see a usage of a variable, we can also try to check if this variable is properly initialized or not. And we can also see that if we assign a value to this variable, which statement will be affected by this assignment. So these are all the things that we can reason about by analyzing the data flow of the program. And here we just do an introduction to data flow, so we don't jump into all the very detailed concepts. We just give you a brief introduction here. And the key concept in data flow is called definition and use, which is also known as def use in short. So define means data. If a piece of data is defined, it means that it's somehow, most of the time, it's related to variables, and it means that this variable is declared and assigned with a value, and then we call it a definition of this variable. And it is considered as used if this variable is involved in some computations for other values in some statements. So in this case, this variable is considered as used. And this is actually the def and use are related to capturing the flow of the information across the program. So definitions often occurs when variables are declared, initialized, assigned values, or received as parameters. So if a function receives a parameter, it is also considered as that parameter or that variable is declared or defined in that function. So this is where definitions happens in programs, and uses happens in programs are in the locations of expressions or conditional statements or any like statements where the variable is used as an operand. So this is use. So let's see an example here for def and use. So here in the first one, in the first line, we can see that this variable min is assigned with value 1. So this is considered as a definition for min, right? What about the second line? It is very straightforward, right? It's just a definition for max. And because we are assigning the value of n to max, so it's also the use of n here. And what about the third and fourth lines? So do we have any definitions in these two lines? We have, right? We have definition for mid, and we have use for min, max, right? And do you think this one is considered as a use for A or a definition of A? It is actually a use of A, right? Because it's not a declaration of a variable. It's not a value assignment, right? So A is just used here. It's not defined here. And the same goes for min and max. So we have the definition of mid. We have the use of min and max. So sorry, I think the first line is here. Yeah. So for the first line, we have no definitions and we only have uses. What about the fifth line? Do we have another def for mid? Yes, right, because it's value assignment. Every time we assign a value, it's a new def. So we have a def for mid, and we have a use of min and max, and so on. So you can just use the rest of them as a practice. And since we have definitions and use for variables, we can try to create, because we want to reason like things like where does the value of this variable come from, or like will the definition of this value affect any usage of it, right? Because we care about the relations between def and use for variables, we can create pairs for def and use for variables, right? So we can say that there is a diffuse pair when these conditions are satisfied. So the first condition is that there must be a def, right? And the second condition is that there must be a use. And the third condition is that there must be a feasible control flow path to reach from location A to B. So because if there is no control flow graph from A to B, then it is infeasible to for the use to actually for the location B to actually use the definition, right? Because the program will never execute in such a way, right? So there must be a control flow graph path connecting to locations. And the last requirement is that the path is definition clear. So this means that definition clear means that so there is no other there's no other definitions in between the path A to B from A to B. So there's no other use in between. So the original value of x at location A is used at location B. So this is the last requirement. And we can use two examples to demonstrate this. So which one, according to this definition, so which one do you think is clear from 1 to 2 and 1 to 3? So which one do you think is clear, is definition clear for x? The first one or the second one? Which one is definition clear for x from the start, from the first statement to the last statement? The first one is definition clear, right? Because for the second one, there is another definition, right? The original value is not kept for the usage. So the first one is definition clear, and the second one is not. However, if we just consider line 2 and 3, then it is definition clear for x, right? So there is a diffuse pair here for 2 and 3, and there is a definition pair for 1 and 2, but there's no diffuse pair from 1 to 3, just because this assignment breaks the definition clear rule. So this is an example of diffuse pairs. And let's try to practice more. So let's try to identify all the diffuse pairs for min. So what we can do is we try to identify all the definitions first, and then we try to identify all the usages for later. So the first one is let's just use here as an example. So let's use the red color to denote definitions and use green color, maybe blue color to denote usage. So you can see that from 1 to 3, there's a diffuse pair, right? Because it is defined in line 1, and there's no other definitions in between. So 1 to 3 is, what about 1 to 4? Is it also? Yes, 1 to 4 is also. What about 1 to 5? Yes, right. What about 1, 6 is mean that it's not appearing in 6, so we don't have anything there. So what about 1 to 7? No, right? Because 7 is also considered as a definition. Yes. So what about 7 to 4? Because there's a loop. 7 to 4. Yes. 7, 5, right? Similarly, we also have 7, 5. And that's all for the diffuse pairs for me. And you can use some other values to practice with this example here. And now, since we have data flow, we have the data flow, right? We have learned how to derive test cases from control flow. But now let's try to come back to the topic of testing. So how can we derive test cases from this data flow as well? So since we have a new concept of data flow, so why don't we just create a new coverage again? So what we can do is we can have two types of coverage derived here based on the concept of diffuse pairs. So the first one is DU pair coverage, and the second one is DU path coverage. So you can see that for this structural testing, is like we are always trying to find some coverage metric. So for all DU pair coverage, you can actually imagine the definition could be very straightforward, right? So what we want to do is we want to cover all the diffuse pairs at least once for every variable, right? So it's very straightforward. So we just cover all the DU pairs, and this idea is that we try to cover the we try to consider how do we execute the statement, or what values are used when we are executing certain coverage. So this actually complements the structural coverage, right? Because even if we achieve like 100% of path coverage, we may not be able to find some bugs. So, but if we consider the values, then we can cover some bugs. So this is why we use DU pair coverage, and it is calculated like this, very similar to all the other coverage metrics. And we also have DU path coverage. So for similar to other, like how we derive other coverages. So DU pair means that we just want to cover each diffuse pair once, right? What if we combine, but we don't care about the combinations of different diffuse pairs, right? So what if we just try to cover all the combinations of the DU pairs for a specific variable? Then we will get DU path coverage. So it means that because one DU pair might go through different execution paths to reach one DU pair. Sometimes, for example, for this while loop here, so from 7 to 4, from this is not a good example actually. So let's imagine there are some other branches after this 7 here. So we may take different paths to get back to 4, right? So there could be multiple different execution paths, right, for getting between the DU pairs. So if we also consider to cover all the potential paths connecting the diffuse pairs, then we can get this DU path coverage. So what we do is what we want is we want to cover all the non-looping paths in between the diffuse pairs at least once. So this is DU path coverage, and as we can see, it is actually stronger than the DU pair coverage, right? However, this also suffers for DU path coverage. It also suffers from the path explosion problem because even without looping, we can have an invisible amount of paths, right? So for example, if we try to find all the DU paths from this, if we try to find all the DU paths from this, so maybe this, then we need to go through all the potential if branches, right? Then this is not a DU pair actually. It is a DU pair. This is not a very good example, but if you can imagine, if we have every time we encounter a branch, we double the count of subpaths, right? So even if there are no loops, because we don't care about loops for DU paths, even if we don't care about loops, we may still have an invisible amount of paths just because of the number of branches we have. So that's how for the data flow coverage. So you don't have to, because in this we are in this course we care more about the coverage metrics for control flow graph. For data flow, you just need to know that it is used to complement the control flow graph based coverage, just because even if we achieve 100% of path coverage, the strongest metric we can get, even if we achieve 100% of path coverage, we may not be able to find bugs because we don't if we don't know like the values we are using to reach certain locations in the program, we may not be able to trigger the bugs. So that's all about structural testing. And let's have a quick recall before we end today's lecture. So in today's lecture, we have learned about the last family of coverage, which is known as path coverage, right? For path coverage, a path is like a sequence of nodes and edges executed from the control flow graph. And every time we enter a loop, we can get a new path, right? Because we are appending new elements into the path, right? So we will have a new path every time we enter the loop. So that's why loops and branches are giving us some invisible amount of paths. And in order to deal with this invisibly large number of paths, what we do is we try to do some partitioning again, right? So the first type of partitioning we can do is we can try to group different paths into different classes, right? So if we don't care about the number of times we take the loop, we just care about the subpath inside the loop, we are doing boundary interior testing, right? And if we just want to try out some specific times we take the loop, we are doing loop boundary testing, right? And these two are related to partitioning the paths according to by grouping them. We can also try to extract segments on the path, right, from the path. So and then combine them together into some patterns for us to create test cases to cover, right? So for that we have LC-SAJ, right? We can create segments and combine them together. And different levels of LC-SAJ can give us different equivalences for coverage, right? So if the level is 1, then it's kind of equivalent to statement coverage. If the level is 2, it's kind of equivalent to branch coverage. And we also learned about the limitations of the structural testing based on control flow information, right? Because sometimes we may not be able to create a feasible test case to satisfy the requirement for the test case design, right? We learned it through the exercise of the second lab poll, right? We cannot create a test case that skips the loop for loop boundary testing, right? And we also another limitation of practical limitation of the structural tests derived from control flow graph is that we are ignoring the values of the variables when we are executing certain piece of code, right? And that could cause us to miss some bugs. And that's why we need the data flow driven testing, right? And for data flow, the key idea is to identify definitions and usages and try to identify diffuse pairs, right? And we can create new coverage metrics based on the diffuse pairs, right? So that's all for today's lecture. And thank you for coming and see you.